Hi, welcome to the Signal Path. In this episode, we're going to take a look at an acoustic camera. This is the FOTRIC TD2, which is their economy entry-level model. An acoustic camera allows you to localize the source of sound pressure waves. And if you combine that with a visual camera, which this also has, it allows you to put it exactly where it is in a scene that you're looking at. It has a lot of applications in industrial and electrical domains, and we're going to take a look at some of those in detail. If I turn this around, I've put it on one of my own tripods over here. You can see the microphone array in the front of this. And of course, it's using a beamforming microphone array in order to find the source of the sound. It can also measure the frequency because it's digitizing all the waves that are coming to it. There's a lot of interesting science behind this. So aside from characterizing it and using it, I also want to take apart and understand exactly how the front-end sensor works. So let's start with that. And this camera has a very recognizable form factor. And at the top, we do have 3 ports, a USB-C, a micro HDMI, and a port for micro SD card. So it's really nice that it comes with a micro HDMI because you can project it on the TV very easily and even record it if you really want to, although it does have its own built-in recording capability. And the USB-C can be used for charging as well as a software in the computer that can take advantage of the data that it is collecting. The battery is in the handle and really has a very basic form factor. Now, the teardown of this unit is pretty easy because the front-end module where all the interesting stuff happens is in one unit. And there's a single cable that takes all of that into the core of the handheld device, where I suspect is the operating system, the display, the battery, and a whole bunch of other things. But what we really want to look at is the front end. That's where the MEMS array is. And I believe what they're doing is that they're standardizing an interface so they can have different front ends with different number of MEMS elements and perhaps more capabilities. I know they have a hybrid version that has both thermal and acoustic camera at the same time, which is very interesting too. And that they can just exchange that and have the same core computer talking to many different heads. And that's a common technique in many instrumentation. I also see that this is made of metal for a few reasons. You do want some rigidity in terms of acoustic characteristic, but there's also heat dissipation. I do see a thermal pad in there, which we will take a look at. So perhaps they're doing some processing locally on there. And we'll take a look. Could be an FPGA, for example. So it's a nice architecture, but I'm very eager to take this part apart and see what it is made of. So with the front end now separated from the unit, we can take a closer look at its individual components. So there's a little board where that's just the interface board to the main body, and it has 1, 2, 3 connectors to it. This goes to the camera, this is just the LEDs in the front, and that goes into the processing engine that looks at all the MEMS signals at the same time. Now looking at the number of pins that are here, and looking at some of the ICs underneath, most likely there's a lot of processing happening there, which we will take a look at. I'm not 100% sure what they're doing here. This looks just like a bunch of passives, maybe some filtering, or maybe there's something under the epoxy that we can't see. But it looks like it's something that they had to add afterwards. It's not part of the main PCB for some reason. So if you now remove this top part and remove all of these cables, we should slowly get closer to the MEMS array PCB. So I've gone ahead and completely disassembled the front-end module of this acoustic camera. Now we can go layer by layer and appreciate the engineering that goes into building something like this. So right now we're obviously looking at the front of the camera. In the middle, there's a hole where the optical camera is. This allows you to image the scene and then combine that information with the direction of the sound to produce an image. This is very similar to how thermal cameras do it. There, they're combining an optical camera in the visible range and a thermal camera infrared, and they combine that, creating a hybrid image. This is basically exactly the same idea. We also have 2 white LEDs that can illuminate the scene in case you're using the actual camera. Now remember that we're trying to find the direction of the sound coming towards the acoustic camera in order to visualize it and ultimately create a picture localizing the sound. Well, this is a perfect application for beamforming phased arrays, which we have looked at extensively on the channel. Generally speaking, for RF beamformers, where we use antennas, we have seen them on a square grid. That's because these rectangular kind of arrays are very popular for RF applications due to their simplicity. Also, the bandwidth that we use there with respect to the carrier frequency is very, very small, allowing very simple algorithms to be used on rectangular grids of antennas. And antennas can also be very well behaved in those situations. But in this case, we're talking about microphones, and the wavelengths are very different, even though the wave theory really remains the same. So, of course, you notice that this is not a square grid. This is, in fact, a spiral pattern, which is very common for acoustic cameras. And of course, for acoustic applications, the absolute frequency you're looking at and sampling is still pretty low, which means that things like alignment, synchronization, and the amount of computation you need to do is significantly more relaxed than it is for RF applications, at least for a reasonable cost. Which means that these other interesting patterns of detectors and microphones are actually not possible because you can process them in real time. And in this situation, if you notice, this spiral pattern has some interesting properties, which helps a lot. So in the center, these microphones are much, much closer together than they are at the ends of the spiral. You can see that these two microphones are much, much further apart. This means that you're doing spatial sampling, which scales with wavelength as you go away from the spiral. And this has advantages because remember that for these acoustic things, you need to look from 50 hertz to 50 kilohertz potentially. So you have 3 orders of magnitude of wavelength. This never happens, of course, in RF applications. So in this situation, this allows you to have this pattern which then spatially samples across a really broad range of wavelengths, allowing you to actually be able to resolve and do beamforming with reasonable grading lobes and side lobes. You can also do multiple captures and other kind of interesting signal processing in the background, again, because the frequency is low, and get some of these ambiguities resolved. You also notice that even though this spiral pattern is fully shown, not all of them have holes in them, which means that not all the microphones are populated. So not only do you have a spiral pattern, you also have a sparse pattern. So only some of the microphones are present. This should immediately be obvious. Why? Because of course it saves cost. Because if you don't have a microphone, you don't have to process a signal, you don't have the MEMS that you have to place in there. So it becomes simpler, the amount of computation is less, but then the more sparse the array, more grading lobes and more undesirable effects are going to happen. At the same time, notice that these microphones are much closer together than the wavelength is. That also has some advantages and disadvantages in terms of beamforming. But overall, this spiral pattern for acoustics allows you to capture this really wide range of frequencies, scan really well, and look at the scene and do some ambiguity resolution through software. So the theory is very basic, in fact. Of course, the engineering implementation to lower the cost is what's interesting here. So these holes are obviously going to let sound through. So we can flip it and see what they're doing to make sure that, well, nothing falls through it. And on the other side, we have a really fine mesh. And this is going to help debris not fall through those holes and be caught with this and easily, hopefully, cleaned. At the same time, it lets the sound through. So yeah, this piece is pretty simple. Spiral pattern of holes. The next piece is the MEMS microphone array, which is much more interesting. And I like this next board a lot because there's some really simple engineering that helps quite a bit in the design of this. So those holes in the front cover are aligned with these vias of a certain diameter, and they're kind of like a little waveguide allowing the sound to go right through it. Now, not all of these are populated on the other side, but all these holes are there. And that's how they pass the sound through to the other side and gives you also a fairly good isolation between the individual holes. Pretty clever. And here's the back of this board, and look at how neat it is. There is a foam tape that covers the entire back for acoustic purposes and isolation and so on, which I've peeled back halfway. I didn't peel it all the way because it was beginning to tear. And you can see all the individual holes. Each hole can be potentially populated with a MEMS microphone, but only some of them are, every one of those silver boxes, and that makes sense again because this is a sparse array. Now imagine you had so many microphones. What would you do with all those signals? Well, you definitely don't want an analog signal because then you'd have to digitize them all simultaneously and it would be a nightmare. So the logical thing to do would be to use some kind of a digital signaling. And I think that's what they're doing over here. Each of these MEMS microphones has 4 pins. I'd imagine one is ground, one is VDD, and one is clock. And the clock is super important because that's what's used to synchronize all of these MEMS for a sampling edge in order to be able to produce a reasonable coherent beam. And that's exactly what this needs to do. The other pin, I believe, is a PDM, which is a pulse density modulation output. Essentially, what it means is that the microphone is going to produce ones or zeros depending on the acoustic wave coming in, digitizing it across time. This is very similar to a delta sigma modulator, which I have done a video on, but essentially these bit streams are going to represent the sound that's coming to the microphone. So now all you have to do is have many, many digital IOs that are all aligned together with the clock so that you can sample all of these microphones at the same time in order to do a coherent beam detection. Very simple architecture. What you're left with are these 2 connectors, one on this side and one on that side, with a lot of IOs, but they're all digital at this point. So now you have to process them. And now the microphone array board interfaces through these connectors to this main motherboard, which has all the processing on it. So on this side, there's really not much happening. There's just a bunch of capacitors for the component on the other side, and all the IO lines being routed down to the center. And of course, what would you use to process a whole bunch of digital signals at the same time? An FPGA. And that's exactly what is here in the center. Now, interesting thing is that this FPGA is a Chinese-made part, and the datasheet is all in Chinese. This is the first time I think I've seen a completely Chinese end-to-end silicon for something like this. And that's exactly what's going on. We do have an FTDI chip and an SD microprocessor here. Those are just basic interface things and probably some management of the IOs to the rest of this instrument. And I think this is just some power supply filtering by the looks of it, because the power supplies are just going to it. some memory here on the side. So all those PDM modulated signals coming from the MEMS microphone arrays go in here, get processed with the appropriate algorithm for the beamforming, and the result of that, which is a direction in space of where the sound is coming from, after it's been fully processed by the FPGA, is then sent through this ribbon cable to the host computer. So the host computer doesn't have to do all that computation. It happens real time here in an FPGA. Now remember, these are acoustic frequencies, so the rate of update is still significantly slower than the computation these things are capable of, and that's why it can do such a sophisticated kind of beamforming on this spiral pattern. Yeah, I have to say I'm pretty impressed. I don't know if anybody from Flare is watching, but this company has a lot of products that compete really well against the state-of-the-art that I see both in acoustic as well as thermal cameras. I'm also really eager to look at the thermal cameras as well, but the competition, it's tough. And the final layer here is our camera with some thermal pads there and the interface to the main instrument. Yeah, that's it. All right, let's put it back together and play around with it. And of course, microphone arrays are just as well studied as RF beamformers are. And in this one example that I found here, they are trying to evaluate the performance of various microphone arrays and configurations of where you put your detectors. So here they're describing a classic beam pattern in 3D space that would come out. This is a bore side pattern from a microphone array. And they have a few parameters that they want to compare. So beam width is an important one, of course. And then they have dynamic range. Here they describe dynamic range as a distance between the peak of the lobe and one of the side lobes. I'm assuming they're also including grading lobes. So you can imagine by making a sparse array or various other configurations of the array, the dynamic range will be affected. The dynamic range would also be significantly affected by the frequency, and we talked a little bit about that. Now, I did mention during the teardown that we could be looking at a factor of 1,000 in dynamic range, but that's very difficult because the array spiral would have to get extremely large. This instrument we're looking at really starts around 2 kilohertz. It goes up to about 60 or 70 kilohertz. That's still quite a bit of a dynamic range in frequency. So if you go down over here, they plot a few things, and then we can continue seeing their measurement topology here. So they have a little chamber they create, and at the end is where the detector is. And then here is an example of so many microphones that they have, and it's a few different patterns. Now, there's a few interesting plots over here. For example, if you look at this plot on figure A, that's at 1 kilohertz. So you can see the main lobe is really fat and wide. And as you go higher and higher frequency, here at the bottom, at 16 kilohertz, the main lobe is a tiny, tiny dot in the bottom, and you see all the other side lobes and effects around it. So we're going to see multiple parameters play at the same time, carrier frequency as well as the shape of the array itself. And this is kind of cool. Here they're looking at a few different mechanisms by which they can order their array, and look at that. This one at the bottom here, that's exactly the pattern that we've been looking at in the instrument we just did the teardown. And then they plot across frequency things like the dynamic range that they're interested in for various configurations. They don't talk about sparse arrays so much in this paper, but you can see that this can be really well studied, and lots of examples of there are. So keep in mind during the testing that as we go lower and lower in frequency, that main lobe is going to get fatter, which means that the precision in which we can localize a sound at 2 kilohertz is going to be much worse than we can localize at 20 kilohertz. And in fact, we will see that perfectly looking at it in measurement. So even over here, you can see in this example, as you go lower in frequency, look how much wider the beam width becomes. So if you want to detect a frequency location here, you just don't know exactly where it is. And then as you go higher, the beam gets narrower, then other things get worse. Yeah, so this should show up in our measurement. Let's try it out. And here I'm capturing the display of the acoustic camera using the micro HDMI output, which is exactly the same thing you would see when you're looking at it. There are a few things you can adjust with the GUI. It's reasonably well polished with some features built into it. For instance, you can select how many measurement points are made at the same time. A single measurement just captures the strongest source of sound. Multiple measurements will capture multiple of them if you want to see several things at the same time. And there's this hologram view, which is showing you kind of a density of sound waves that is superimposed on the actual camera itself, which is pretty helpful too. Over here, you can adjust a circle, which you can control the size of, where it allows you to do spatial filtering. In case you have a very noisy environment and you don't want to capture sound outside of that environment, it just limits you to the source of the sound there. What it's measuring right now is probably some reverberation around the room, and we will see some of that during the actual measurement. And then we have a couple of adjustments over here. You can add some spot measurements. There's also this thing, which is distance. I still can't figure out exactly what this does. It doesn't seem to make much of a difference. The manual is a bit cryptic because it tells you by selecting this, it will calculate that, but maybe that's for a different higher end version of the camera. This one doesn't seem to do much with this information. At least I couldn't figure out what it's doing. There's some palettes you can adjust, just like a regular thermal camera has equivalent ones. This is just an acoustic version of that. And then we have a couple of settings over here as well, which I've enabled all of them, showing the frequency configuration, which we will get to. The manual is a bit cryptic. Some of these things aren't really actually explained in there, and hopefully they can make that manual a little bit better. Now going back over here, we do have some dB sound ranges over there. We can also select the frequency range in which this instrument can actually analyze. So audible sounds from 2 to 20 kilohertz, default is from 10 to 50 kilohertz, and the ultrasonic is 20 to 65. So the frequency range goes fairly high. These higher frequency ranges above what we can hear is very, very helpful in industrial applications, because there's a lot of things that make sounds we actually can't hear in our audible range, but are still pretty important to localize, electronic components included, which we will get to. Now, one nice thing is that you can bring this down. You can see a bit of an FFT of what is measured. So obviously my voice is being captured at the bottom, but this is right now not reacting to it because that window is not choosing that. Now you can actually control the size of this window, and you can move it up and down, which is pretty helpful, or you can select one of the default ones. So I'm just going to go to default. That's a nice feature, and it would be nice if the peak was kind of shown, so in case there is a specific sound that can be easily overlaid, but that's a nice little function over there. Now look at this. I can bring my hand in front of it and just rub my finger, and the sound from that is captured. Not what you hear when it's jumping to my wrist, that's just my voice bouncing off of my hand. This is super quiet, but it still catches it. If I do this, you can see where my finger hits my hand. It catches that. That's pretty impressive. It's very cool. So now that we kind of see how it works and what the GUI looks like, let's set up some controlled experiments and see its behavior. So I was in the process of setting up some experiments with known audio sources, and this was my work area. And no matter what I did, there was always a point source of sound coming straight out of the table, right around over here. And sometimes if I put my hand, I can make it disappear. And of course, now that I'm talking, it's going to jump around because my voice is interfering with it. Well, where do you think that's from? Well, if you look at the spectrum, it gives us some hints. Here's the spectrum. If you look carefully, just underneath 42 kilohertz, there is a peak. There's a whole bunch of peak at lower frequencies also when I'm talking, but that's just from my voice. If I stop speaking, you can see that 42 kilohertz tone or so remains. Anyway, I couldn't produce that frequency with my voice in any situation. Well, a little bit of hunting around, and it becomes clear where it's from. And let's pick up the instrument from the tripod and look around a little bit. And check it out. Here it is. It is coming from my lights. And that is not surprising because these are DC-DC converters, and there's always going to be a coil whine coming from the DC-DC converter circuits. Now this is at 42 kilohertz, is beyond what I can hear, but if you dim these, the frequency actually drops, and sometimes it is within audible range. There's the last one over there, and there's over here, and there's the other one. Yeah, so consistently it is that. So it's another example of just accidentally finding something interesting, and then from this we can tell that these indeed do emit some sound around 42 kilohertz or so, and it also explains why they become annoying when you dim them. Pretty amazing. And in fact, with this camera we can discover a whole bunch of things that have this whine noise. So here's my USB charger bank. Look at that. That's also doing it. So this one seems to be around 25 kilohertz or so, and it seems to have a more spread spectrum clocking. Now you always see that 42 kilohertz or so because that's from my lights. That's always going to be around the room. So yeah, so this is why this filtering, that this range that you can change can be so helpful, because if I put it up here, you can see that it cannot detect it anymore because it's outside of that. It's just picking up all the noise randomly around the room. But if you bring it down within that range, it picks up that sound. So it's extremely helpful to be able to do this frequency discrimination. So it has both frequency discrimination and spatial discrimination by being able to look at a certain zoomed area. Both of those are very helpful. If I change that to this mode, you can see that, yeah, that is the source of the sound. Very cool. Anyway, let's not get distracted. Let's go back to some control testing. And here's the setup that I want to use. We're going to use the Siglent arbitrary waveform generator, the STG7000 series, which is very capable, and I've done some videos on this in the past. It's connected to two speakers. One is hanging over here, and then one is stuck up here. Both of these speakers are driven from channel 1 and channel 2 of this arbitrary waveform generator. Now we can generate any kind of signal we want, both spectrally pure as well as having noisy content, and we can see how well this acoustic camera can localize them across frequency and spectral content. And by the way, this signal here in the corner, that's still from the lights, just bouncing off the surface of everything. It's very difficult to completely get rid of it in this room, but it doesn't matter. What we can do is we can limit ourselves in this test to audible sounds, and that completely removes that because it's outside of the audible range. And then now we can play with the speakers within the range we can hear before going into ultrasonic experiments. Now, there are always some sources of audible sound in the room. It's impossible to make it quiet, especially if I'm talking. But I'm going to start from 2 kilohertz and work my way up in terms of the tone. Some of those tones are going to be a little bit annoying, so hopefully it doesn't show up too much on your speakers. Now, keep in mind that as the frequency goes down, it's harder and harder to detect its direction given the size of the microphone array that we have. In fact, this is rated down to 2 kilohertz. The other thing you need to keep in mind is that the spectrally pure tones, which we're going to start with, also pose their own challenges because they reverberate and create constructive destructive interferences, and it can be quite difficult to localize them like that. So let's go and try this. So this is now 2 kilohertz. I also have the spectrum down there so we can track it. So here's 2 kilohertz. You can see that it can't really find where it's coming from. It clearly knows something's going on because it stops moving around. But let's increase the frequency. Here's 4 kilohertz, and if you look carefully at the bottom, you can see the 4 kilohertz tone. So it thinks that it is over here, even though the source is here. Let's see what happens if I move this around. So you can see that it is indeed aware that the sound source is coming roughly from that region. I tried changing the distance, it didn't make any difference. So let's go higher. So here's 10 kilohertz. So at 10 kilohertz, it has a much better time finding it. Yep, it's working much better. And you can see on the screen clearly the 10 kilohertz tone. And we can increase that. I can go to the upper range. Here's 20 kilohertz. Now, I'm too old now to be able to hear this, but it's indeed finding this, no problem. Here we go. Yep, it's definitely there. Now the speaker should be able to put out some sound above 20 kilohertz. So let's go over here and change this and put it into this default up here. There it is. You can see the tone very, very clearly. Let's see how much higher we can go with this speaker. So here's 25 kilohertz, very strong tone. Yeah, now it has absolutely no problem finding it. So it definitely works a lot better at higher frequencies. Again, that's normal because of the size of the aperture. If the spiral could continue and become twice as big in terms of surface area, or 4 times as big in surface area, then it would work even better. But of course, then it becomes much larger. So that's a normal behavior. Now, for most applications, like finding leaks and other things, there is high frequency content. So that's not surprising that this is really intended for those applications given its size. But yeah, the spectral measurement is working very well. So let's now try multiple sources and tracking them. So I have set the second channel to a frequency close to the first one, 22 kilohertz versus 25, and I'm going to enable that, and then let's see what happens. There it is. So right now you can see from the spectrum that there's 2 tones, but right now we are in a single tracking point, so it's just grabbing the louder one. So let's change that mode into multiple tracking. Look at that, it has no problem. It detects the one up here, and it detects the one down here. In fact, if I pick this up, and move it around, you can see that it's tracking it. And at some point I can make it get confused a little bit when they're really close together. Yeah, we're asking too much of this. It's going to certainly get confused, especially with spectrally pure tones. That's a very, very tough case. Almost nothing naturally is this pure in terms of tone, but yeah, it has no issue tracking that. Now, we should make sure that when we move it, it can also maintain that, not just moving the source, but also moving the camera. Here we go. Going a little bit this way. Yeah, look at that. Now going up and down, azimuth and elevation for the beamformer. Look at that. It's always so amazing because obviously I cannot hear these, but they're there. Yeah, it does a pretty good job. So now let's try a square wave. A square wave has many harmonics, and therefore you should have an easier time detecting it because there's so much more audio information available. So right now I'm generating a sinusoid at 3 kilohertz using this top speaker, and you can see that just like before, it has a bit of a difficult time finding it. Let me put it back onto single point. Yeah, so it sometimes gets confused. It doesn't know where it is. But if I change this from a sinusoid to a square wave at exactly the same frequency, now it has absolutely no problem finding it because it has so many harmonics, and you can see those harmonics in the frequency content itself. And indeed, it's tracking it just fine. It's pretty annoying sound, but indeed it makes sense that the higher spectral content is going to make it track no problem. So now let's give it a very difficult situation. Imagine you're trying to find some kind of a leak. Now these are very broadband hissing sounds. Well, we can emulate that by creating a noise spectrum coming from the instrument itself. Now I have set this to be a fairly quiet hiss, so let's see if we can detect that. And if you look at the spectrum right now without me talking, you can see that there isn't much audio information there. So if I turn this on, you can clearly see that around 22 to 33 kilohertz or so, there's some sound coming, and that's very similar to what a hissing sound would be. So it finds that without issues. Yep, that looks good. But what if there is another leak that's significantly louder? Will it superimpose on top of the other one? So now imagine that in the spatial domain, both of these have very similar waveforms. They're just noisy, and it has to figure out the source of each one completely separately. So here you go. The second channel is much louder. There you go. But look at that. It has no issue finding both of them, and it can track both of them. And we can also convince ourselves that the source at the top is significantly louder than the source at the bottom by going into the other mode. And look at that. That tells you everything you need to see. So that's much, much louder up here. So it would be a much bigger leak, for instance. And this is much more quiet. And if I turn the top one off, you can see that that becomes the dominant source. Again, the signal over here, that's from the lights. Over here, that's the lights, and that's our leak emulation. Pretty amazing. I'm really impressed with how well these things actually work and how fast it works. Yeah, pretty nice. And in this next setup, I have a vacuum pump over here connected to a length of hose. Unfortunately, somewhere along the length, there is a very, very small hole, and that's difficult to see and very difficult to hear, especially when the pump is running, because it's significantly louder than anything else around it. At the same time, this is a low pressure system, meaning that whether it's positive or negative, a lot of noise is not made when there's a hole. It's just going to be a very, very gentle hiss somewhere along the length. Now, this is a situation where you cannot submerge this thing, for example, in water to see bubbles, because it's a vacuum system and it will suck in the water into it. And in many places, you cannot do this, especially in, let's say, medical environment. So we want to see if this acoustic camera can actually localize the location of the hole. So I have brought the pump within the field of view of the acoustic camera to really give it a hard time. Right now the pump is turned off, and this point that you see around here or so, that's still my lights. So that's also interfering with it, so it's really giving it a tough time. Let's go ahead and turn the pump on. Like so. Okay, so this is now the most dominant source of the sound, and I'm looking at a single point measurement. So of course it's going to measure the sound coming from the pump itself, and that makes perfect sense. But what I can do is now I can turn on the focus area. We can go over here, and then we can change this. Change this one. So now we have a focus point. And if I go over here, that's in the center, that's the pump. Then I can now search along the pipe itself. And look at that. Check that out. Let me see which one is it. We can separate them until we find it. Is it this one? Yep. And that's our hole. Look at that. I can block it. That's indeed where the hole is. Look how well it tracks it. Now remember, there's a lot of noise in this scene, but he has no problem finding it. So even in this situation, when we're looking at the entire image, I could have removed that, and then I could have changed this to the hologram, and we can kind of get an idea that there is something going on in this area. Actually, I can put my hand on it. You can see it goes away. So even in this mode, we can get a pretty good idea that something's happening. So it's really ideal for finding this kind of issues. They also do have an Analyze IR software, but it seems to only be able to connect to their IR cameras live for now. But it can analyze the pictures taken by this acoustic camera. So here's an example of one that I took in the utility room, and you can see that it has highlighted this radar pump. These radar pumps run very, very fast and therefore create a lot of high frequency sound. So you can see it's very easily detectable. There's also a few other pictures that I took from various things happening around. So for example, here's the little pump that is feeding the boiler, and you can see that that is also being detected as it is running. And you can do all the familiar changes and overlays, just like the software would be able to do directly on the camera. It's nice that it retains all the information, like the frequency content, and you can even play back the sound. So it captures that and it's embedded in there, so you can see what the noise was coming. In this case, it's a sound coming from this high-speed motor inside of this. So the software is reasonable. It would be nice if it was expanded to actually include and be able to connect live to the acoustic camera as well and do live measurements. I'm sure that's coming. But for now, you can analyze the pictures that is taken. And there you have it. I hope you enjoyed this review of the FOTRIC TD2 acoustic camera. We saw its capabilities in electrical systems, in electromechanical systems. Definitely can be handy if you're working in that space. If you were a subscriber of the channel, you know that we don't just review something for its functionality. We also want to understand the science behind it and the teardown and the principal operation, because that's half the fun. And I hope you enjoyed that as well. Let me know in the comment section, and I'll see you next time.